All right, so now that we've talked a little bit about forces and motion, we can take the next step, which is to kind of build a catalog of forces that we can use to eventually lead into quantifying motion. So in this pre-lecture video, he goes through and he does a quick little demonstration of a few different types of forces, or a lot of different types of forces that we'll talk about throughout this unit. This was just a nice little conceptual introduction, and later on, as we get into chapter 5, we'll get a quantitative explanation or a quantitative definition for each of them. So the next part in chapter 4 is to take a look and just talk about a few different types of forces that we can use to start to describe dynamics and describe the motion that will occur because of them. So the first one we're going to talk about is the force of gravity, otherwise known as an object's weight. Now, weight and gravitational force are interchangeable. However, if you recall, last unit we talked about how free fall acceleration is not gravity, it's acceleration due to gravity. Well, that's because gravity itself is a force, and the gravitational force is just the pull of an object because it's near the Earth's surface. We call that an object's weight. So the weight of an object is completely under the influence of gravity. And you've probably heard that before, where you weigh different amounts if you're on the Earth or if you're on the moon, and that's because of the gravitational force that's being exerted on you. In this case, the agent for the weight is the entire Earth pulling on the object. Now, once we get into chapter 6, we'll talk a little bit more about the concept of the gravitational force, but for right now, that's all we really need to worry about. When we're taking a look and examining weight, as I can see in this example to the right, weight is always just straight down. It's straight down towards the center of the Earth or straight down towards the ground. And we talked about projectile motion, which is an extension of free fall. That is exactly due to the force of gravity. So we'll also examine a little springs or an elastic force. I just refer to it typically as the force of a spring, but there's all types of springs, and we'll take a look at a couple different types. But essentially, a spring always wants to be at what I like to call its homeostasis. And the best way that we can think about this is kind of thinking about a rubber band. When I stretch out a rubber band, it wants to go back to the way that it was. Same thing if I stretch out a spring like a slinky, it wants to go back to how it was. So whenever it's deflected from that homeostasis, it'll try to go back to being its normal way. So some springs can be stretched, some springs can be compressed. If I think about like the shocks on a car, those springs get compressed and they want to push back out, and that helps us get a more even ride when we're in a vehicle. Anytime that I have something that's attached by a string or a rope or whatever, if it's pulling on an object, it is a contact force that's pulling on that object, and we refer to that as the tension force. The direction of the tension force is always in the direction of the string or of the rope, compared to the spring force, which always opposes the stretching or compressing, which we'll talk about more later. If we examine more closely, this one gets kind of weird, but there's another force that people often either forget about or they struggle understanding, and that's the normal force. And the normal force just means that anytime that there's an object that's on a surface, gravity is pulling it down. So if gravity is pulling it down, why isn't it going down? And the short answer is the surface is pushing back up on the object. It's called the normal force because it's always perpendicular or normal to the surface, and it pushes straight up. So the normal force, it's the force that's exerted back up. And if we think about it in a different way, we have this picture over here. If we think about all the molecular bonds holding atoms together on a table, if something is on top of it, then those bonds are being stretched and pushing back up. It's kind of a weird thing to think about, But imagine holding a ton of books. If you're holding a ton of books, there's a weight force pulling down on your arms. Your arms have to do work, or they have to push back up to stop those books from falling. The normal force is what's responsible for objects being solid, and we use the letter N for the normal force. In this case, the skier here is actually going down in a slope, but like we said, the normal force is always perpendicular to the surface, so it goes straight up off the surface. It's not straight up. If it were straight up, it would, kind of looking at the skier, it would be like this, but instead it's perpendicular to the surface, so it's always normal to the surface, and that's how we should think about it. Next we have friction, and friction is a huge concept in physics. So friction, it has anytime that there's two surfaces in contact with each other. And we'll talk about a few different types of friction as we go through this class, and definitely quantify it. The first type is the friction when anything's in motion, and that's known as kinetic friction. So kinetic friction, we use the symbol F for friction, the lowercase f, compared to how we always use capital F for a force. And kinetic friction is anytime an object is in motion. We use the lowercase f with a K subscript. So if something's like sliding across the floor, it's in motion, we call that kinetic friction. Kinetic meaning just that, kinetic is in motion. Later we'll talk about kinetic energy, next unit. And kinetic energy is the energy associated with motion or associated with having a velocity. The other type is static friction. Now static friction is a little bit different. We still use the same convention where we call it the lowercase f, and then we use a subscript S for static. The way that I remember static friction is that it's always stationary or stuck. So imagine a car parked on a hill. Gravity wants to pull it down the hill, but there's brakes with the car, and those brakes are providing static friction so it doesn't slide. Now, when I think about moving a large object, such as a fridge, I have to push really hard to get that fridge moving, but once it's in motion, it tends to stay in motion. It's actually much easier. And the reason is we start with static friction. So we have to, when we're moving, we start with static friction. We have to break static friction and get to kinetic friction. And we'll talk about those two more in depth when we start getting into the quantification. So friction, whenever we're categorizing it, it always opposes motion. So in this case, this child has a velocity going to the right, which means that my friction is going to the left. So the direction of the vector of the force always opposes the motion. Right here, we have a tension force going to the left because she's pulling with the rope, and then we have the static friction. In this case, it's not moving. The reason it's not moving is because she's a woman. But we have static friction opposing the pull to the left, and in this case, these two are equal and opposite. And we'll talk more about that later as well. The last one we always like to. Oh, it's not the last one, but the next one we'll talk about is the last one that will really quantify this unit. And it's a really interesting and honestly, I feel fun one to quantify, and that's drag. And now, drag happens in a lot of different types of fluids, and fluids is a very loose term. Air is a fluid, water is a fluid. No matter what, if there's an object moving through a fluid, there is a drag force, and that's because the object has to get those fluids out of the way. If I think about like dropping a marble into a bucket of water, or in this case, dropping a leaf onto the ground, similar to kinetic friction, the drag force opposes the motion. For us though, however, except for a couple small times that we talk about it, you can neglect air resistance in all problems. There's a couple times that we talk about it, but that is it. It's really difficult to quantify, and I think I've spoken to this before, but just to kind of give you a quick little introduction, the drag force It's got a very complex formula. It's 1/2 rho times the drag coefficient times the cross-sectional area of the object times the velocity squared. You get all that? Awesome. So in that, we have this concept of the velocity squared. And with the velocity squared, we're going to talk later that forces cause acceleration. Well, if forces cause acceleration, that causes a change in velocity. So the more velocity that I have, the more drag force that I have. As this goes up over here, this goes up over here. And therefore, it changes as a function of velocity, and it gets way too difficult to quantify without calculus. So we're not going to. We have thrust. Thrust is a force. It's a very simple one that it just occurs as an action-reaction pair, and we'll talk about that later. But as an object like a rocket exerts a force downward, it goes upward. So it's exerted by the exhaust gases pushing down. So it's a force that's opposite in the direction of the motion. And you could think of like if you had like any type of jet propulsion, that's going to use this thrust. And that actually falls into the category of conservation of momentum, which we'll talk about in a later unit. The last ones aren't ones that we'll talk about too much right now, but we will get into later, and those are electric and magnetic forces. And these are, like gravity, they're range forces. So they exert over a long distance and not as a contact force. And both of them work because of charged particles. And if you take AP Physics 2, we talk more about what magnetism is. At the end of Physics 1, we will talk about the electricity portion of that. But it does get a little complicated. It has to do with positive and negative charges, and it's something you might have learned a little bit in chemistry, but we'll definitely take into more consideration here. Okay, so we have our quick little catalog of forces. We got one quick check. A ball rolls down an incline and off of a horizontal ramp, ignoring air resistance, so we're ignoring that drag. What force or forces act on the ball? Well, as it goes through the air, we've talked about this already. This is free fall acceleration, so the only force is the weight of the ball acting vertically down, the force of gravity. All right, so the next quick check we have, we're looking at a steel beam hanging from a cable as the crane lifts the beam. And we're going to get into free body diagrams next, but if I identify the forces, well, there's gravity pulling the steel beam down, and then there's tension that's holding the steel beam up. So there's gravity and there's tension, and those are the two forces that are acting. Finally, we got one last one. We have a bobsledder pushes her sled across horizontal snow to get it going, then jumps in. After she jumps in, the sled gradually slows to a halt. What forces act on the sled after she's jumped in? Well, since she's in the sled, she has to have some type of weight, or the gravitational force of weight. The snow is pushing back up on her, causing a normal force. And there is, if she's slowing down, that means that there's friction occurring. So there's kinetic friction, the friction of motion that's causing her to slow down. So with those three things, we ask ourselves, is there a fourth one? And in letter E, it says the force of the push. But we're looking at after she's jumped in. So she has motion, she has a direction of motion, let's say to the right, and friction is acting to the left. It's opposing her motion, but there is no force actually of the push. So this is actually not right, and D is the correct answer. So the next thing that we're going to do is we're going to start making free body diagrams, which is a way that we can visualize forces. So last unit we drew pictures so we could start to analyze motion. Now we're going to draw free body diagrams so we can analyze forces, and we'll do that in the next segment.